have to have Emilia Margoni giving a talk on knowledge transfer, the theory building, and appraisal.
So first of all, let me thank the organizers, Annika, Baptiste, and Chris, for having me here, and it's a great pleasure to share this work in progress with you. So actually this work, well, it's a collaboration with Professor Emilia Margoni, started quite some time ago. We did, I think, 2 or 3 years ago, but as many often things develop, still under development. And recently we turned to focus a bit on the issue of theory building and appraisal. So, to just provide you a very rapid outlook of what we'll be discussing about. So, knowledge transfer very generally relates to the circulation and the arrangement of ideas, models, methods within different disciplines or within the same discipline. And recently, from a broader philosophy of science perspective, there's been a renewal of interest in this kind of transfer, and in particular on the nature of these kind of transfer, their applicative potential as well as their limitations. So in the present talk, I will very briefly go through the taxonomy that so far been developed to tackle this kind of transfer. I will then look at a very interesting, very rapidly, but very interesting cross-fertilization process from a case study in physics, namely the birth and development of neuronization group methods. And then I will briefly talk about this notion of cluster transfer as a fruitful way to account the way in which this cross-fertilization took place in this case study. And I will finally discuss the relevance of this kind of generalized analogical reasoning to evaluate the perceived worthiness in fundamental physics programs. And in particular, the case I will look at is the phenomenon of geometrogenesis in quantum gravity. So, as already said, knowledge transfer is a phenomenon which is meant to capture the way in which ideas, methods, and methodologies get transferred, both within a single discipline or across disciplines. And of course, the underlying assumptions, which is something which can be debated, is to what extent and what kind of taxonomy can we fix the notion of a discipline. But leaving that aside, the current debate on the topic is very much concerned, of course, with the explanatory role of mathematics, the notion of representation, as well as the relevance of analogical reasoning, especially for interdisciplinary transfer. And the main focus is the relevance of mathematical models versus physical theories in the fertilization process among diverse research areas. Why is it the case? Well, as you know, analogical reasoning is very old and has been applied ever since philosophy, say, but current discussions, a very contemporary discussion, is very much shaped by the works by Humphreys, and he was the one to emphasize, which is something, of course, we can debate, but I tend to agree with, and the basic idea is that this kind of transfer among different disciplines, if it relies upon scientific theory, seems to be based on an underlying assumptions about the way in which sciences are related to one another. So scientific theories typically represent the favored candidates to encode scientific knowledge, and so the applicability of this kind of this intertransferability seems to be based on the assumptions that science are somehow organized hierarchically. And on the other end, mathematical models have the advantage to display a, so to speak, higher degree of plasticity, which doesn't seem to be based on these underlying assumptions between sciences. So that's why it's been particularly analyzed in the last few years. And in particular, Humphreys was focusing on this research question, namely, how can a single form of representation be successfully applied to multiple scientific domains that prima facie have very different subject matters. And of course, this kind of transfer in all over the place in physics, biology, economics, and so on. And as I said, recently there's been a renewal of interest among philosophers of science in exploring the more detailed aspects of this kind of transfer, and in particular, F and Lishtandra have focused on which are the conditions to allow model transfer. Nutil and Lötges have been focusing on the kind of informative content that can be secured throughout this procedure, and more recently, Tan has explored also the relationship between model transfer and broader discourse on scientific realism. So in the present context, our focus was not so much how a single purely formal representation can be applied to different contexts, but rather our interest, especially coming from the case study that we looked at, was to see how a collection of concepts, models, and methods was transferred and in virtue of what. And so, as I said, the case study is the development of generalization group theory, and the concept we think captures this kind of development is the notion of cluster. So this can be very rapidly because you're all very familiar with this. So analogy is the general comparison between two or more systems which are thought to be similar in some respects, and of course an analogy works and is used because the underlying assumption is that there are also differences involved. And analogical reasoning is whatever reasoning that is based on the construction of specific analogy. But then more recently, philosophers of science have tried to develop a more refined taxonomy to account for specific case study of cross-fertilization among different disciplines. And in particular, Humphreys introduced the notion of template, which is in this definition are formal patterns, devices, and techniques which can be applied across different research fields. And of course, template transfer is a reasoning based on transferring formal or computational devices untied to any particular object, system, or domain. And recently, Nutila and Lucas have developed the even more refined notion of model template, which is meant to capture the abstract conceptual idea underlying this kind of transfer, and model template transfer is reasoning based on this kind of transfer. So, as I said, analogies and logical reasoning has been used ever since philosophy, or even before so, but a very relevant contribution that is recognized nowadays is the work by Esse in 1966, in which she emphasized the distinction between what she called horizontal and vertical relations. So horizontal relations are what two domains have or not have in common, whereas vertical relations are relations which are connected to objects within a certain domain. And then the debate has been focusing on how, based on a certain analogy, can we then produce a robust, sound, analogical reasoning. And there's been different proposals, as in the case for theories, there's been different standpoints. So Gentner was more for what is called now the syntactic view, in which inferences can be based on purely formal similarities between these different domains. But more recently, as the no shortcut by a syntax expression quite explicitly emphasizes, the idea is that we need to account for more integrated ways to account for analogical reasoning. So to go to some examples, and in particular to go to Humphreys' terminology, as we said, a template is a formal pattern, device, technique which can be applied within different research fields. Then there are subtle differences which are not necessary here, but some examples that he provided are Laplace's equation, Poisson's equation, or the diffusion equation. And in particular, in his intention, these templates represent cross-disciplinary vehicles of modeling, and in particular patterns in his work that can serve as a common starting point for the development of a product, but they can be adapted for the purpose at hand. And on his view, the condition for application of a template is that we need to somehow provide or add to the template some kind of locally constrained interpretation. So this is where you get from a template to a specific model. So when you get from, I don't know, the diffusion equation to a specific application of the diffusion equation. And the condition for transfer for certain kind of templates in his view is that you do not have an interpretation beyond the mathematical one. And this is because then you can indeed provide what is sometimes referred as a kind of resanctioning of the meanings of the terms figured in the template in order to make a locally sound interpretation. The notion of the template has been then recently defined by Mutila and Lucas because they were dissatisfied with this notion of template provided by Humphreys, as Humphreys was very much emphasizing the role of this formal aspect that could be rearranged across different applications. And being dissatisfied with this idea, they started to develop a broader concept, which they term model template, which they define as an abstract conceptual idea and which is associated with particular forms and computational methods. And of course, this is to be defined on the basis of certain mathematical structure, which intertwines with specific methodologies and with specific computational methods. And the way in which they provide the definition of a model template is that you need to categorize the constituents of the model, and to do this, you need to specify all this set of characteristics, such as the mathematical structure, the ontology, the prototypical properties and behaviors, the core conceptualizations of the template, and the paradigmatic problems to which the template can be applied. And of course, as you can imagine, the typical example that is cited in this kind of transfer is the EASY model, which was this model that was developed in the 20s, started being developed in the 20s in order to account for the ferromagnetic to paramagnetic transition, and it represented a starting point to then develop other very interesting and very relevant model or model template in their own words to describe completely different phenomena and context. So the shedding complete cyclic model has been applied to study spin glasses, I think, and the Kuramoto model has found very interesting applications in the context of neuroscience. And the idea is that you can start with the EASY model in which you know how to interpret your degrees of freedom, but then you can resanction the meaning of these degrees of freedom in order to account for other clustering phenomena, other collective phenomena. And so that's how these models were then developed. And so in the case of the EASY model, the abstract conceptual idea that they're thinking about is this general cooperative mechanism which is leading to clustering and phase transitions. And of course then you have a number of theoretical and computational templates which are associated to this very broad conceptual idea, which is, for instance, partition function, energy function, probability distribution, and whatever, based on the case study you're looking at. So, so the reason why we started focusing on this topic is because we crossed through a paper that Emilia Margoni has provided, in which they precisely discuss the use of the EASY model in both physics and socio-economic systems. And basically the argument was that there is a difference between interdisciplinary and interdisciplinary model transfer, which led to this fact. While the EASY model, according to them, provides a useful play a useful explanatory role in the context of physics, once you start broadening the application of this model, for instance, to explain socioeconomics phenomena, then you start having a sort of a thin analogy in which the explanatory role gets somehow lost. And the specific case study they were looking at was a phenomenon of segregation, urban segregation, in which, again, the variables that you use in the EASY model, which are conveying the value of the spin, gets reinterpreted in a socioeconomic sense, and they showed how some kind of collective phenomena happened in a certain urban area in which, I don't know, a certain kind of population was living. And the point was that, in this case, the adoption of the EASY model is not meant to be accorded an explanatory role. So, why is that so? According to them, the interdisciplinary transfer of the EASY model, so the application of the EASY model within the sole domain of physics, is justified, of course, on the basis of universality considerations, which is the very widespread way to justify this kind of transfer within a single disciplinary framework. And that these kind of universality considerations do not extend to the socioeconomic case. So our two main goals, starting from this work, was that of somehow trying to complement and lead their analysis by a more refined inspection into the birth and development of RG methods, which is what typically is described as providing an explanation for the definition of the EASY model, and to evaluate the role of knowledge transfer, this kind of cluster transfer that we introduced, to evaluate the pursuitworthiness of progress in fundamental physics. So basically, we were not particularly satisfied with the sole argument based on which the interdisciplinary transfer is justified using these universality considerations. So why RG? Probably I shouldn't be saying this here because you all know that, but renormalization group are very powerful tools in contemporary physics with a very interesting cross-fertilization history between quantum field theory and statistical mechanics from the mid-50s to the 1970s. And the other reason why they're particularly interesting, or they've become particularly interesting also in philosophy of physics, is because they are deeply intertwined with the emergence of the effective theory approach in the 70s. And end of 60s and beginning of the 70s. And of course, there's a lot of debate, a very interesting and lively debate, on the theoretical import of RG methods for issues such as emergence, explanation, reduction, and so on. So this will be very, very sketchy. We can go back to this in the Q&A eventually. But to put it very, very naively, the problem that mathematicians and physicists were dealing with already in the 30s and the 1930s is that right from the beginning, quantum field theory has been plagued with the presence of infinities. So what is now called the old theory of renormalization was introduced precisely to try to deal with this kind of infinities. And well, there was a conventional strategy that was developed by especially Tomonaga and then of course Feynman in 1948, which is based on the idea of introducing a cutoff to try to provide a way to observe the divergences in some approximation and then eventually removing the cutoff. But then this initial idea, this idea of providing a way to deal with the infinities arising in quantum field theory has been developed much further, and also from an interpretational standpoint, the cross-fertilization between quantum field theory, statistical mechanics, and condensed matter physics provided a new way of thinking about renormalization. Because in the old theory of renormalization, which is in terms of interpretation very much shaped by Feynman's standpoint, the idea was saying that the only theories that should be accorded validity were the ones in which, once removing the cutoff, you could still have a renormalized theory. So there was a strong attachment to what the cutoff means in terms of interpreting the theory. And so the cutoff was interpreted in what is now termed a formalistic sense, so something that should be eventually removed. But the cross-fertilization process that we crossed through was suggestive of another way of interpreting renormalization and renormalization group. And actually, very important results in the 50s were by Ernest Tückebeck and Andre Peterman, who introduced the notion of normalization group theory. Then, well, Gelman and Lowe's work for the discovery of QFT scale invariance is typically considered as the starting point, the most, as Weinberg called it, one of the most important papers ever published in quantum field theory. So it's typically recollected as the most relevant starting point for the development of normalization group methods. But this is also for historical reasons, because the paper by Tückebeck and Peterman was in French, so there was not much recognition of that. But then Bogdanov and Shirkov provided the connection between the previous works, and in particular they introduced the term renormalization group. So this is very much in what one would call the field theoretic renormalization group developments, while the other strands, if we can call it this way, is very much related to the theory of critical phenomena, phase transitions, and this was particularly developed in the 60s by, first of all, Benjamin Witham, who provided what is called a scaling law in the neighborhood of a critical point. A very much important work is Kenneth Wilson, who provided what is now interpreted as the first prototype of an effective theory. And then, of course, the very much famous Leo Kardanov's block spin strategy to account for the way in which a system near criticality behaved. And then Wilson in 1969 and also in 1971 provided an amalgamation of what we may term the field theoretic strand and the condensed matter physics strand, put it very naively. And Kenneth Wilson, in particular in 71, provided the basis for the current conception of renormalization as, in Ross expression, an expression of the variation of the structure of physical interactions with changes in the scale of the phenomenon being probed. And it's very interesting because in the context of statistical mechanics, the goal of renormalization group methods is to provide an explanation of the cooperative behavior and universality for systems in which correlations somehow become particularly relevant, while in high energy physics, the goal was to provide an explanation for the distinction between what are now termed effective theories, so which sometimes one refer as breaking down in the ultraviolet limit, from fundamental theories, which are meant to hold to the infinite range of scales, thanks to phenomena such as asymptotic freedom or safety. So looking back very rapidly at the historical developments, the same term renormalization group has been adopted and used for highly different connections, applications. And so, in particular, what is relevant to outline is that most of the time in statistical mechanics, or at least in for the case of the theory of critical phenomena, but in most condensed matter physics applications, what you're interested in doing by using RG methods is to provide, is to concentrate on low energy effective physics. Whereas on the other end, in the field theoretic problem, at least in the old theory of normalization, the problem was that of trying to push the UV limit and see what happens there. So the two research focuses were more, are divergent in this sense, because in statistical mechanics, the goal is to work on mesoscopic scales or low energy scales, whereas in high energy physics, the problem has to do with short distance behavior. So schematizing, one can think about two main strands, what I call the field theoretic, well, not I call, what is identified as the field theoretic strand, which deals with the standard apparatus of quantum field theory, and the discrete version, which is this sometimes referred to as Kadanoff-Wilson approach, which is characterized by the introduction of new concepts and calculational tools to provide a sort of post-graining or zooming out procedure. So the question, the leading question is there at the general level something which is common to all these approaches, despite these different aspects? And there's a very interesting recollection of the physicists that play the role, both by going through the original papers and by going through the recollections of their works, in which what is sometimes referred to as the renormalization group zoology, precisely to capture this kind of variability and different applications, is still characterized by a deep conceptual unity which somehow underpins the various applications. And in particular, we can think about this leading idea from a methodological standpoint as a way to try to discuss and to show how, given a certain physical system and given a certain scale of interest, one can reduce and somehow single out the relevant degrees of freedom for that scale. And of course, this is why the relevant property is typically referred as critical scaling. So in this sense, the renormalization group can be thought both as a way of thinking and a calculational tool. And as I said, the field maturity and also its interpretation found its birth, especially in connection with the theory of the critical point in transitions. And it's interesting because, again, formally, the field theoretic approach and the Kadanoff-Wilson approach appeared as very different, because in the field theoretic applications, what you're actually using is what is referred as a group structure, whereas in the discrete case, as you're doing some kind of coarse-graining procedure, what you're dealing with is a semi-group structure. So formally or structurally, these applications are not identical, but conceptually, we can somehow lead a sort of deeper understanding in terms of what Benz et al. Call the statistical nature of the critical universality. And in particular, it's very interesting to go through some other recollections provided by Johannes Inyo, who's a theoretical physicist based in Sapienza in Rome, who actually worked in the development as well of renormalization group methods, in which he explores the role of analogy, and in particular, analogical reasoning in theoretical physics. And for what concerns the case study that we are looking at, typically analogical reasoning can follow different multiple paths, say, but from a conceptual and structural standpoint, one can look for structural similarities among different research fields, as was the case for certain applications in quantum field theory and statistical mechanics, or one can focus on between purely formal aspects such as mathematical or statistical results and specific applications. And so the two examples that he mentions are the introduction of spontaneous symmetry breaking, which happened as a kind of cross-fertilization process from condensed matter physics to quantum field theory, and the theory of critical phenomena with the adoption of RG methods, which is interpreted as it's a bit more complex, but it's interpreted as an application from quantum field theory to condensed matter physics. So in the second case, the theory of critical phenomena, what you get is that you get this formation of large islands in which a new phase for systems near criticality form. And the strategy developed by Kadanoff is the box spin strategy, in which you show that the more correlations extend over macroscopic distances, the less relevant it becomes to consider the original microscopic system. And in Johannes Inyo's interpretation, well, this is more technical and complex. The idea is that apart from the conceptual similarity, he wanted to show that Kadanoff's analysis represents a simplified form of what is referred to as the multiplicative RG equations, which are displayed in the context of quantum field theory and statistical mechanics. So these aspects created, according to Bionalasigno, and indeed going through the papers that seems to be the case, represented the starting point for the construction of an analogy between critical phenomena and renormalization group as applied in quantum field theory. So our question is then, are the notions of analogy, template, model template sufficient to account for this case study and for the way in which the cross-fertilization process happened for the development of our two methods? Well, it looks as if, at first sight, indeed, one can adopt this Mutil-and-Lunge's argument based on just simply saying that it is renormalization group methods which justify which explain this model, which justify the application within the sole domain of physics. But if you go to closer inspection, this kind of compatibility can be somehow challenged. And I think Bionalasigno from this standpoint is particularly relevant because he provides some kind of roots that were particularly relevant to allow this cross-fertilization process. And these details are not that relevant, but he provided some kind of a connection between critical phenomena and probability theory. He describes renormalization of derivation of mathematical statistical results, and in particular the central limit theorem. And he also goes on to explore, again, this idea of the existence of a multi-capillary structure, which is associated with the transformation on the probability distributions which are induced by the block transformation. And more generally, the impression is that in order to account for the kind of import and transfer that was happening in this case study, we need to account for a more general cluster of ideas such as critical scaling, universality, order parameter, correlation, and so on, which is not to be confined solely to a formal or solely to universal arguments. Right, so, but then what can we do with these notion of quantitative transfer? How can we make these notions useful, or at least as a conceptually valid entry point to debates in philosophy of physics and foundational physics? Well, our impression is that the notion of cluster and transfer, and so this generalized notion of transfer in which you different conceptual and methodological aspects somehow intertwine, can be particularly fruitful in the context of theory building and appraisal, and in particular it can play a significant role for the debate on pursuit-worthiness. So the context is the recent renewal, again in the broader philosophy of science community, I'd say, on pursuit-worthiness and its significance in scientific practice. So, as you all know, the preliminary distinction was provided by Loudon in 1977, in which he focused on the distinction between the context of acceptance and the context of pursuit. And in Loudon's understanding, based on the bifurcation provided by the 1938 book by Reichenbach, in which he provided this distinction between context of justification as opposed to the context of the discovery, Loudon puts the distinction between acceptance and pursuit in the context of justification, and of course this can be debated. But typically, this is rephrased in the following sense. So the context of acceptance is the context in which scientists choose to accept a theory and thus to treat it as if it were true, whereas the context of pursuit is a context in which scientists evaluate whether there are good epistemic reasons to pursue, to follow a certain specific inquiry or research line, and in particular which theories should be further pursued in scientific inquiry. And in Loudon's words, he wrote, "I have proposed distinguishing sharply between the rules of appraisal governing acceptance and the much weaker and more permissive rules or constraints that should govern pursuit or employment." And again, he also wrote, "More generally, there's a whole spectrum of cognitive stances that scientists can adopt toward their theories, suggested by phrases like entertain, consider, and utilize as a working hypothesis." And so his main suggestion is that accept and reject are about two extreme points on this spectrum, and that we should allow for this extension of the kind of theory assessment. So that's why the notion of pursuit-worthiness should play a role. So a theory is typically considered, again, as pursuit-worthy to the extent it can be shown to have a promising potential, for instance, to contribute to certain epistemic goals that could determine eventually theory acceptance. And of course, to be pursuit-worthy is sometimes referred as to be promising, to exhibit a certain potential, and so to project an expectation of epistemic success in the future. And so, of course, there are a number of issues related to how can we then make use of this notion. And the first issue relates to how do we identify perceived worthiness criteria, how do we establish which research lines to investigate. And this is a very relevant aspect in scientific inquiry and philosophical theorizing. And a proposal on which we can go back to this kind of proposal that it's sometimes referred as to the economic account proposal, in which basically what you want to do is to provide a balance between epistemic benefits, such as empirical accuracy, explanatory, predictive, and unificatory power, and expected costs, such as economic costs, temporal resources, and instrumental costs. And the other issue is how do we have to think about the relationship between perceived worthiness and influence to the best explanation? Are these just a way of thinking about the same way of producing inductive arguments? And also, which kind of theory appraisal is to be associated with the notion of perceived worthiness? Is it, as Loudon suggested, only a form of epistemic appraisal in the context of justification, or is it to be used, as Cabrera suggests, mostly as a heuristic kind of tool to establish what research lines to follow, or should we think about a more intermediary position between discovery and justification? And so in particular, another point is to argue which kind of motivation is offered by perceived worthiness criteria. And according to Fleischer, this represents some kind of non-evidential epistemic reason. Right, so our point on this is that reasoning based on knowledge transfer, and so analogical reasoning, abstraction, unification, as may be quite unsurprising at this point, provide good reasons for pursuing a specific research line. And as the renormalization group case shows, this type of reasoning, especially since based on, from our standpoint on this notion of class transfer, is particularly fruitful in theory appraisal, both in the form of heuristic, as when the application from quantum field theory to condensed matter physics was established, as well as epistemic, in which the general framework of RG methods was being interpreted at the end of this in the 70s, after this very intense cross-fertilization process was taking place. And so the renormalization group case can also be used as a case study in which you can somehow outline the role of perceived worthiness in both theory building and theory assessment. Now, I'm not sure how much time I have.
Now at 32 minutes.
Okay, good, perfect. So then our aim was then to try to see how this can be put in practice in specific currently under development programs in foundational physics. And case study I'm focusing here comes from quantum gravity, and the other example which we would like to concentrate, which we have not so far done, is the case of supersymmetry. So here, the case study, as I said, arises from quantum gravity, and in particular, the phenomenon of geometrogenesis. So the general context is quantum gravity, and in particular, the now very vibrant and very successful emerging gravity paradigm or approach, as different physicists and people working on this topic may like to call it. And in particular, within this context, within the so-called emerging gravity approach, in which very naively the idea is that we need to think about GR as emerging from an underlying behaviorally dissimilar, potentially ontologically dissimilar set of degrees of freedom. And so the scope in this context becomes to provide an understanding, provide a motivation to fill the explanatory gap between quantum gravitational degrees of freedom and continuum relativistic space-time. So within this very highly diversified and highly prosperous and interesting emerging gravity class of approaches, let's say, an hypothesis that has been explored and that I found always very fascinating is the so-called hypothesis of geometrogenesis, in which again, put it very naively, the idea is that space-time is meant to emerge from a phase transition, from an underlying structure which do not display the characteristics which are typically pictured and captured by, for instance, general relativity. And, well, the history is a bit longer than this, but for what concerns quantum gravity applications, the introduction of the concept was mostly emphasized in the context of cosmology by Hu in 1995. And his idea was that of trying to provide again some kind of analogy, and so some kind of analogical reasoning between statistical mechanical systems, and in particular Bose-Einstein condensate and the universe. And the general suggestion was that a fruitful way to develop further this emergent gravity approach was to somehow start importing methods from other research areas of physics which were not sufficiently, according to their standpoint, adopted in order to explore this underlying quantum gravitational environment. And so the suggestion by Hu was that there could be a very important cross-fertilization, again, or transfer, if you want, of the methods which were prospering in condensed matter physics for unresolved cosmological questions. And the successive refinements by Hu were in 1996 and 2005, in which he proposed to Bregon to think about general relativity as the hydrodynamic phase of a quantum gas. So within the context of quantum gravity, the first remarkable employment dates to 2006 with a so-called quantum gravity model, which is really a toy model, in which they provided a background-independent model characterized by two phases, respectively encoding low and high temperature regimes. Now, this model, as I said, is a toy model. It's very simplistic, and there are some critical aspects that have been emphasized, in particular relating to the existence of some kind of thermal bath, which allows the definition of the phase transition, and this seems to create some problems with the kind of temporal development that should not be supposed in the underlying structure, but of course this relates to the way in which we think about quantum gravity. And then further development were provided also in the group field theory framework, which is a specific approach to quantum gravity, and in particular by Oriti in 2007, and also, of course, more recently. And so the idea is that what's referred as cosmological singularities, such as Big Bang or black holes, may signal the breakdown of the phase that we'll recognize as the hydrodynamic phase, and so the break of the continuum hydrodynamic-like description of space-time. And so the idea is that the coming into being of the universe, and here we have experts who've been working on this, may result out of a condensation process among underlying quantum gravitational entities, which in the group field theory framework, non-group field theory framework, are sometimes referred to as agents in space-time. So very rapidly zooming in the group field theory approach, the question becomes how should we explore this kind of condensation process? And there's nowadays this research line which is referred to as the condensed cosmology program, which is actually not to be confined to the group field theory approach. At least that's not how they want it to be, because of course also in this case they're very much relying on universality arguments, so the expectation is that you can have this kind of condensation process across different models and across different frameworks. And what is interesting is that technically what this requires, so to explore this kind of condensation process, you need to import the tools from statistical field theory and especially the renormalization group machinery. So again, the notion of cluster transfer and knowledge transfer as arising from the specific case study we were thinking about becomes relevant. And some recent discussion are provided by Oriti and Pitis and Sakellariadu for cosmological applications. So just to provide like a very general way of thinking about this, so the case study is the phenomenon of geometrogenesis. In this case, the source is represented by Bose-Einstein condensate systems. There can be other analogical kind of analogical systems, but that's what they've been mostly focusing on. And the target in this case is space-time, the universe. Of course, this can be debated. And of course, the basis for the knowledge transfer that is implied in this case is the microscopic structure of Bose-Einstein systems on the one hand, and the microscopic structure of space-time in the other. And the kind of inference you want to try to construct is basing on, on the basis of the hypothesis that there's some kind of connection between the microscopic structure, then you want to provide an explanation for the phase diagram of the atomic molecular structures as leaving some insights on the phase diagram of the quantum gravitational entities. And the employed machinery to do this is typically mean field and renormalization group methods. So again, to account for this kind of condensation, you need all these conceptual and methodological tools, to say, such as collective behavior, critical scaling, universality, and so on. So the critical aspects to justify, well, we have experts here that have been brilliant on this, but the problem here is that we would like to understand to what extent this kind of analogy is sound. And of course, there are some critical aspects associated to this kind of analogical reasoning, because the basis for the construction of the analogy is that we're assuming that both that quantum gravitational entities somehow display some kind of atomic and molecular structure, which can be put in connection to standard atomic and molecular structures, and then we want to, on this basis, construct our inferences. So the critical aspects are the underlying assumption related to discreteness, and what motivation do we have for this assumption? Well, different motivation have been provided, physically justified motivation, such as UV completeness, find a value for black hole entropy, or no photons of infinite energy, but also critical remarks on that standpoint. And also the other problem, which relates to a certain of these problems, such as group field theory, which is sometimes referred to as pre-geometric, is that what kind of discreteness is at stake, because quantum gravity in this sense are not just the spatial-temporal entities, right? So how should we think about the discreteness of these structures? And sometimes we can think about them as quantum gravitational entities being countable or carrying finite properties which are encoded in the group elements labeling quantum gravitational entities. And the question is, are these conditions sufficient to render the analogy with atomic molecular structures sound? Well, we believe that, of course, these kind of analogical arguments provide motivation to make the condensate cosmology program pursuit-worthy, but it does not allow straightforward confirmation, precisely because these aspects, these underlying assumptions are quite robust and quite, not uncertain, but problematic. So why pursuit-worthy very rapidly? Well, the idea is that we can have some kind of increased understanding. So quantum many-body physics can represent a useful test bed for classical and quantum gravity to explore issues such as equivalence principle, quantum unitary, to provide predictions in unfamiliar regimes, so phase transition and under control condensed matter systems as heuristic tools, for instance, for the development of quantum gravitational phase diagram. Possibly reduction of expected costs for new research program, and this relates, for instance, to trying to track contexts in which possible experimental validation is to be watched for. And of course, also more generally theory building and appraisal, in the sense that we can have useful insights on back systems as a basis for non-negligible inductive support for emergent gravity. But of course, this is on the debate, and so this is related to what Evans and DeVos called inductive triangulation, or NAPO's inductive view. So why not straightforward confirmation? Well, because of the modal character of the analysis, which in one case, to accept a certain analogy being robust, is actual versus expected. For the scope, in the sense that on the one hand, we're looking to validate whether a certain theory is to be accepted or not, while with pursuit-worthy programming, we're just looking for useful or relevant research lines. And also criteria of success, which seem to be quite strict in one sense and more versatile in the other. But of course, we can also speak still about a modest degree of epistemic support, in the sense that, of course, this should be based on then trying to find some phenomenological signatures, such as the one analyzed by Liberati, in which he explored the fact that there's a general expectation that emergent theories of gravity would be characterized by the existence of either extra fields, which may possibly lead to Lorentz breaking, or by the presence of some degree of non-locality. So, of course, this phenomenological signature is what would make the difference between confirmation and just adding that this research line is pursuit-worthy. So to close very rapidly, the renormalization group case calls for a family of concepts and unions, which is neither secured, we believe, to the balance of explicit, naming empirical, or implicit versus formal similarities within different fields of inquiry. But we think that a more composite family of and core union transfer is called for to account for this cross-fertilization process, in which both formal and conceptual elements intertwine, following very interesting multiple cross-fertilization paths. And we finally discussed the relevance of cluster transfer as a useful basis for arguing in the favor of pursuit-worthiness of specific theoretical problems in foundational physics. And here is a quote from this.
some comments, and I've chosen to look a little bit at the last part of the presentation, exploring this connection between knowledge and cluster transfer and the role it plays in pursuit readiness, which I hope we can talk about a little bit more. So, in general, when we want to evaluate whether or not, or which theories to explore, research lines to pursue, you mentioned when we took the economic account, where we're constantly having this cost-benefit cost-benefit analysis, trying to figure out whether it's worth it to pursue a certain research line. So there are, of course, these kind of different, very broadly speaking, these different things we can consider. So the epistemic value of something, whether it has potential to increase our knowledge and understanding of things going on. The practical, whether there are application and benefits that we might get from this potentially. And then, of course, we need to make sure that this it's not too costly, considering what we might get from it. And then values, whether this is something we even care about or we consider important. And as you were talking about, it's really a complex issue that can look really different in many different contexts. So it's a huge issue to figure out how we're supposed to evaluate this in general. And from your talk, it seems that, if I understood correctly, the contention that you're trying to suggest is that we can, reasoning based on knowledge transfer can provide us some good reasons for why we might want to pursue a certain research line or not. And you use this case of the development of renormalization group methods. The development of this to show how knowledge transfer plays an important role in the development of new theories. And you introduce this new notion of cluster transfer, which is supposed to really give us a very strong sense of knowledge transfer from one regime to another that has a lot of ideas with it. So this is knowledge transfer is supposed to provide us really good reasons for why we might want to pursue a certain research line. And of course this is super useful, especially in case of quantum gravity, where we don't maybe have access so much to epistemic, not epistemic, but we can't go out and test measurements so much, so we need to figure out test measurements we cannot go out and measure very well, so we need some other criteria. And in the case you give here for geometric genesis, you're saying that we can use, when we want to investigate condensation cosmology, we can use knowledge transfer going from those Einstein condensates and how we can understand and work with these kinds of systems to try to make sense of the entities, quantum entities in image and space-time. And from your slides, you sort of give these different reasons why this might be useful, or why it might provide us good reasons. So increased understanding, how we understand those Einstein condensation systems, can help us think analytically about the quantum gravity entities. It might help us with predictions, maybe when we try to develop these kinds of things, because we can take what we know from here. And then reduction in expected costs. I'm not quite sure what that really means. I suppose it's that compared to if we had to start completely from scratch, we have a good way to begin. And then this idea of potential inductive support that could be very useful in quantum gravity. So this is sort of we can see that these sort of give reasons that go back up into this cost-benefit analysis, economic account, that these are all very good reasons why we might want to pursue this kind of reasoning. Now I wanted to try to take a step back and ask a little bit more about this connection and the scope to which we can use knowledge transfer and cluster transfer to give good reasons for the pursuit readiness of something. And what I was thinking about is, once we have our set of assumptions about where we want to start and some candidate theories, it seems that all candidate research line we might have will have some degree of knowledge transfer, because that's how physics usually works. And then I was wondering how here the degree or the extent to which we have knowledge transfer plays a role in discovering or deciding which research line to pursue. So a question we could ask is, should we use cluster transfer as a criterion for evaluating the pursuit readiness of these different candidates that we have, and if so, to what extent? And the first answer could be like, no, maybe not just this cluster transfer. It's not just that we have potential for cluster transfer that's makes it pursuit-worthy, and if that's not quite the case, that means probably there are some underlying reasons why we might want to pursue or not. Are these some additional factors we want to consider when we are evaluating these questions? Or maybe we just say, yes, it seems that maybe especially in quantum gravity, that here when we have the potential for cluster transfer, that this gives us really good reasons and we want to do this. And then I suppose one thing I could ask about or could wonder is now then, do we want the maximum amount of knowledge transfer? Like if we have a really good reason to think we can have a huge amount of knowledge transfer in one of these candidates, is that the one we should be most eager to pursue? That could be the sort of thing. Or maybe it's something in between these. Right. And this sort of brings me to this idea of when we want to develop new theories, we of course want to find this balance between knowledge transfer and maximizing this, and then new innovation where we generate new knowledge, I suppose. So it's a complicated issue, a fine issue, I suppose. So on one side, lack of conservativeness can result in underutilized scientific knowledge that we already have. But I'm also worried that the overemphasis of knowledge transfer might divert attention from potentially very different kinds of research. So I'm worried maybe if we always just want to maximize and only ever prioritize the kinds of candidates that maximize knowledge transfer, that we might delay actual new innovation. Put very strongly, of course, I'm sure we'll look at there at the end. But if every time we have to choose, we always choose the one that transfers most of what we already know, we might be holding on to maybe frameworks that potentially are not so good in new domains. So I guess the upshot is I think that cluster transfer and knowledge transfer in general, they do seem to provide good reasons why we might want to pursue this certain research line. And I think what we see from the case you gave us is that knowledge transfer is a really good marker for when something is pursuit-worthy, but also that maybe there are some underlying criteria of pursuit-worthiness that we might also need to look at to evaluate this, and therefore that cluster transfer and knowledge transfer is maybe only a part of the picture. And I would like to invite you to maybe say a little bit more about how cluster transfer fits into this. So to summarize, I have these 4 connected, related questions. So the one I already stated, should we use cluster transfer or knowledge transfer as a criteria for pursuit-worthiness? And how does it relate to potentially other considerations? And if we focus too much on cluster transfer, do we risk like an over-conservatism where we might be holding ourselves a little bit back? And then also whether you think that pursuit-worthiness in quantum gravity differs a little bit from other cases where we might have access to different kinds of empirical confirmation. So, okay.
Good, great. Those were great questions. I'll try to go through them so what I think about them. So, starting with the first one, should we, you said very different things on which I'm now thinking about, but let's use your summarizing to try to go through them. So the first question is, should we use cluster transfer as a criterion for pursuit-worthiness? Well, yes, I guess that was part of the old point, and but the notion of cluster transfer, you're perfectly right, relates to some broader discussion on how we should construct analogies in analogical reasoning, and to what extent analogies and analogical reasoning are meant to provide criteria to establish the pursuit-worthiness of a program. And then, of course, in this sense, I think a very useful way to think about this, I don't know if this is useful, but I think essay work on this is quite relevant, because as I said during the presentation, she provided this distinction between horizontal and vertical relations. So horizontal relations is what different systems across different domains may have in common, while vertical relations are those that are related within the same domain. And so you may have some kind of hypothesis on your source system, and S stands for source, of course, and T stands for target. So horizontal relation is a relation that I expect to have between objects between different domains. So for the case study that we're thinking about, maybe the case of geogenesis, and the hypothesis may be the notion of discreteness. So in the sense, the discreteness of standard molecular and atomic structures on the one hand, and atomic-like or molecular-like structures in quantum gravitational degrees of freedom. And this would be called a horizontal relation. And indeed, we try to discuss that this assumption can be, it's based on a number of mathematical and physical justifications, saying, but that the whole point resides here. And then you want to infer some possible consequences. So from knowing the structure in the source system of the atomic and molecular atoms and molecules, or atomic and molecular structures, you may want to construct your, your phase diagram, your different possible phase transitions, and you use, in this case, mean field theory or normalization group methods, depending on the kind of phase transition or situation you're dealing with, to justify the construction of this phase diagram. And then the question becomes, is there some kind of analogous structure in the quantum gravitational phase diagram? And so your point is, should we use cluster transfer as a criterion for pursuit worthiness? I would say that these translate into a way of thinking how much our horizontal relations are robust, and how much the presence of these horizontal relations then justify the adoption and the realization of vertical relations, and so to construct this phase diagram, for instance. And so again, for the case study that we're thinking about, you have on the one hand, well, if you think about Bose-Einstein condensates and space-time as Bose-Einstein condensates as a source and space-time of the universe as the target, then you want to provide some motivation to account for the relationship between hybridynamic variables on the one hand and cosmological variables. So you can consider the total number particle, the energy momentum, the energy density on the one hand, and you can have scale factor or other parameters in the cosmological case. So the more you can justify the connection between them, the more you can operate in the sense. And the idea is that as this kind of construction here is based on the adoption of RG methods, for instance, the more you can justify the robustness of this analogical reasoning, the more you can, and so to justify the connection, you need to be based on analogical reasoning and so in this sense on cluster transfer. So that's why if that is the case, it looks as if that kind of research problem, such as condensed cosmology problem, seems to be worthy of pursuit, or at least that's the way in which I think about it. Then the second point was, how does cluster transfer relate to other considerations of pursuit worthiness? Is it the case here that you're trying to say that we need to think about possibly other reasons to pursue a certain research line, and what would then be the impact or the import of... So is it the case that you're trying to think that maybe cluster transfer becomes relevant because you think a certain problem is pursuit worthy despite of the explicit presence of possibly transferring some machinery? Was that your...
So I think that those three questions that are quite connected to each other. So the worry would be that if we only look at this cluster transfer potential, and that's the only thing we use to evaluate whether or not we should pursue something, that then I was worried that there might be a risk that we're too conservative usually if we just try to keep understanding the world in the way that we already understand it somewhere else. So I was wondering if there's other considerations that you need to take into account. If we think that cluster transfer should be one of the criteria that we're looking at, we're deciding whether or not to pursue one research line over another.
Yeah, I think that makes, that is perfectly, I think that is perfectly right. And indeed, one of the advantages I would say of, well, we call it cluster transfer, but we can think about this broader notion of knowledge transfer as a useful way to apply this idea that if you just think about applying a certain physical theory to broader context, then you may be relying on conservative argument. But as long as you are mainly focusing on methodologies, and especially methodologies which arise from statistical mechanics, which are very much related to probability theory or to how to deal with many body physics, so a huge number of degrees of freedom, it seems to be a case in which you can use this kind of what Humphreys maybe, or what Dylan Ludwig would call model template to explore research areas without being that conservative. And indeed, it's been on this point, I think there's been a very recently a very interesting thing that I came across, which was an article published by Carlo Rovelli on discussing the pursuit word. Well, it doesn't speak about pursuit worthiness, but it basically was speaking about all the effort that has been put in trying to work on supersymmetry, and the idea, what he was trying to suggest is that physicists have been too much led to try to explore these routes, which seem to be quite innovative and quite unexplored, instead of focusing on the physics that we know of. And it's interesting for me to see that actually cluster transfer seems to be a case in which, despite being some kind of conservativeness in the sense, it's quite open to novel paths. And indeed, one of the case studies we wanted to look at is precisely supersymmetry. So I found it interesting to see the way in which different context allows to think in different ways to these programs. So yeah, and of course there is. I think there's always this risk of conservatism, and I think the whole debate, which becomes particularly interesting in the case of quantum gravity, is precisely to what extent do we have to leave a space to this conservatism, or to what extent we need to explore possibly different routes, and of course different approaches of very different ways of framing this point. But because one thing that one could say that we didn't talk about in this context, which is related to cluster transfer, is to what extent this kind of application is that subject to the no alternative argument developed by Stanford. So this idea that at each moment of historical development in whatever discipline, whatever scientific inquiry, we can always think about all the possible alternatives which are completely different from the one that is actually taken as the accepted model of theory or program, which then eventually may become to be taken as the correct one throughout the span of time. And so this kind of risk probably is at stake in this kind of argument. But again, I think that being very broad and being highly relying upon statistical methods, it's sufficiently flexible, say, to allow for innovative aspects. Of course, then you need to look for specific case study. So that's why I was mentioning that a quantum gravity model is really a toy model, because there are some other underlying assumptions which would not strictly derive from this clustering transfer.
I would suggest maybe that we open for the general discussion. So if you have a question, please raise your hand. Let's start with Vera. Please keep your hands up.
So, thank you very much. So this is very interesting, very helpful. And so I'm not an expert on these things, and therefore my questions are very general. So I have two questions. And one is, what notion of model of theory do you need here? Because, I mean, if you apply, I don't know, the rules of classical logic or standard probability theory to different domains, that wouldn't count as knowledge transfer as you're thinking of it here. So I was just wondering whether you had some demarcation criteria for that. And my other question is, concerns the notion of pursuit-worthiness. So you told us something about pursuit-worthiness, and I'm just wondering whether you would additionally need something like success criteria. So it might turn out that something is pursuit-worthy according to your criterion, but eventually it doesn't succeed. And I was just wondering what you would make of that.
Thank you very much. So, yes, for what concerns the first question, I think this is to be evaluated on a case-by-case basis. So in particular, the models that I was talking about, this easing model and identification to the Champéry model and Kuramoto model, what you do is that you, well, starting from the easing model, you construct your Hamiltonian, you fix you make a number of assumptions about the way in which neighborhood spin relates to each other, and on the basis of this Hamiltonian, you then construct what is called a partition function, which is a way to describe, to account for probability distributions, and on the specific assumption, you can show how this partition function eventually leads you to the appearance of certain clustering phenomena. I don't have a more, I don't know what you're specifically thinking about when you think about model theory, but the entire point was that of trying to specify that indeed you cannot just rely upon some kind of structural mapping between these applications. And the case study of this very fancy methodology, which we refer to as renormalization group theory, is a particularly interesting case study in which you are not supposed to rely upon this kind of structural similarity. And the reason, well, depending on the context, is because in certain applications you may have a proper group structure, whereas in other applications, such as the one in condensed matter physics, you do not, because what you're doing is what we refer to as the coarse-graining procedure, so the inverse property of the group does not apply. So I guess that's part of the reason why we think some broader notion of knowledge transfer is required. I don't know if you want to say something on that. And for what relates to the pursuit-worthiness debate, of course, it's a very lively, it's a very diversified debate. And the general point of Loudon was precisely that of saying that we need to somehow enlarge what we would take as possibly justified. So to enlarge peer assessment, evaluation criteria, but of course in the debate on perceived worthiness, then you also have success criteria. So it's something you need to consider. Actually, you can also see whether or to what extent all these can be formalized, and typically what they try to do is to put this kind of criteria in a Bayesian framework to justify the pursuit of a certain research line. But yes, success criteria maybe are part of the picture, but are not the sole criterion or the leading criterion. Or let's say, when I talk about prospective, I think I use prospective success, that would be relating to this success criteria that you were referring to. But the debate is very differentiated. So the people were not that focused on that aspect, and but there are people who have been concerned about that because, for instance, even the issue of having a certain research line to be testable is not necessarily a criterion to make it perceived worthy, right? Precisely because it's very likely that we can test hypotheses which are false, right? Thank you.
Alyssa?
Yeah, it's really interesting. In the part about the phase transitions and the geomesis thing, I was expecting you to return to the discussion about analogies or whatever there. I mean, but it kind of dropped out. Like you were talking just about like, well, we're using these kinds of frameworks from statistical physics and thermodynamics, but I thought that you were going to need, maybe I just don't understand what the thesis is or how it's being argued for. Like, I thought you needed to like justify that this was appropriate, because I mean there are clearly cases where there are like inappropriate analogies that then people get upset about. Like the one I was just thinking of was the one, like the Higgs boson, that like infamous one with where it's like the popular person at the party that everybody's like attracted to, and then you get this kind of analogy that then I guess was like helpful at a certain point, but then is misleading. I don't know if I don't work in this kind of epistemology, so maybe there are better examples, but I thought, there are some cases where analogies mislead and they're like giving you false accounts of what's happening, even though they're sometimes like very attractive and people like them. And you didn't say anything there. I just wanted to say a little thing. This issue of conservatism came up. People bring this up a lot, and I just feel like if we're Bayesians, being conservative is totally reasonable, right? You have a kind of you have like background knowledge that's been well confirmed, and then because of your priors, it's going to take more evidence for you to, right, stop believing in that, and it's like completely rational. So I think, yeah, in general, I wouldn't worry about that. I feel like that's just being a good Bayesian. It's like how, yeah, so I don't, yeah.
Yeah, perfect. Thank you very much for your questions. So both concerns, the first one, I'm sorry, maybe I was too quick in general in the second part, which was actually
Oh no, I just
interested
invite you to say more. Yeah.
Okay, yeah, sure. Yeah, no, the whole point was that of trying to say to what extent are we justified in the case of in the case study of geometrogenesis to draw these analogies between standard molecular atomic structures typically encountered in condensed matter physics, and in particular the typical solar system, as I said, is Bose-Einstein systems in different configurations, and on the other end these quantum gravitational degrees of freedom. And the kind of, say, motivation that is typically discussed is the one that relates to this notion of discreteness. And so there have been a number of both mathematical and physical reasons that have been discussed and provided here. I mentioned some of them because these are taken as robust and also discussed here. So there's this notion of unique completeness, on which we also have a critical remark by our very Niels and Karen, and also this issue of finite value for black hole entropy, which our very Chris also discussed, and this idea of there being no photons of infinite energy. So as I was saying here, as you were perfectly suggesting, the point is to what extent are we justified in making inferences based on this kind of analogical reasoning, and what we call here the Q, this kind of hypothesis, we call it however we want, this kind of hypothesis, the more you are likely to show that this is somehow robust, the more you can be confident that the kind of inferences that you draw are meant to be robust as well. And so the kind of connections in this case, in the case of geometrogenesis, is highly reliant upon this idea of underlying atomic and molecular structures. And you can provide some motivation for that. And then, as I said, this is a bit critical, both because these arguments can be criticized from different angles and standpoints, or have been criticized from different standpoints, and because it's not exactly clear what notion of discreteness is at stake in pre-geometric context, so in context in which we seem to be lacking at least standard spatial and promotion. But of course you can try to, using again analogical reasoning, provide some kind of a way of thinking about a discrete structure as defined in mathematics, and so to think about mathematics. Well, you can try to see how to think about discreteness in a context which is not necessary to be attached to spatial temporal motions. And this is what, for instance, people working in group field theory may think when they think about discreteness. But this is what would constitute the the starting basis for the construction of the analogy. And then, of course, you can, on this basis, then eventually provide some kind of vertical relations. So, I mean, the case study that you were mentioning, and also here Chris and Niels have been working on the problem of applications of analogical reasoning to open graduation, so that is a typical example that is discussed. And I think on this we totally agree that these kind of arguments, what we term knowledge transfer or whatever, seem to be, in the sense, not straightforwardly confirmatory, but, as we said, suggesting the pursuitworthiness of this research program. But I'm not sure I fully addressed your point, because, yeah, you said that you wanted to see how analogical reasoning is playing a role in the case of geometric genesis, right? That was
Yeah, so you're saying it was the discreteness?
Yeah.
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 You're saying there's reasons for discreteness, and then, because this was like based on an atomic theory at some point, that was assuming a discrete, okay.
Yeah, of course you can draw other.
Yeah, I guess, yeah, it was, I don't know, I brought up the bad case because I thought, yeah, maybe it's helpful to contrast like with like a bad case where this is like going wrong, and then saying like, but see, this is different, you know, I don't know.
Yes,
it's supposed to be friendly.
Yeah.
I have a clarificatory question that is, I think, related to this, namely, so you discussed someone, I might have misunderstood what was going on, but I think this person dismissed a certain analogy or transferring to economics because certain universality considerations didn't apply, but they did apply in the domains of physics where this transfer was made. So but you didn't discuss universality later when you discussed the transfer to quantum gravity, and then I was thinking maybe the kind of argument Alyssa was looking for was saying, yes, we have these sort of universality considerations, broadly speaking, that do allow us to make the transfer to quantum gravity, or a general argument to say maybe actually sometimes we can do without that, but that seems very difficult to read for me.
Yeah, no, thank you very much. Yes, so the universality arguments are used also to extend the Ising model to socioeconomic phenomena. The point is that what is the import of universality, broadly speaking, and what is the import of universality argument in that context? And of course, also in the case of applications or potential applications of quantum gravity, universality arguments are the main point. I guess I would say that also for all this debate on analog gravity, seems to be the case that universality arguments are relevant. And of course, it's interesting to see, well, universality is a very broad concept in physics, which is applied in very well. The underlying idea is that in certain contexts, we can discard certain degrees of freedom and just focus on certain other degrees of freedom, very broadly. But then more technically, and especially related to renormalization group, these are some more technical meaning, and indeed the kind of universality that is expected in the condensed cosmology program relates to the second kind of universality, which is very much related to the presence of RG fixed point, for instance. So of course that would be relevant in the application to quantum gravity.
So could we say that a good analogy is one that's it's worth checking whether there might be a university class, even though we don't know. So it's worthy of pursuit to check if there is a university class. In this example given by Alyssa, there is no reasons to think there is a university class, or at least it's deceiving, the X case.
Yeah, I think this is a very nice way to frame this.
Okay, Chris?
Thank you. So I think this is a great project, very interesting, thank you. I really like Larry Loudon's distinction between the context of acceptance and the context of pursuitworthiness, where acceptance, to remind everybody, means accepting or treating a theory as if it were true, whereas pursuit-worthy just means you have some justification for the theory, but only to the extent to which it's then rationally acceptable to sort of invest resources in the further elaboration and development of that research program. And I think it's a very important distinction that needs to be maintained. And when you talked about geometric genesis at the end, you very clearly made that distinction as well. And you sided with the right side of that debate, I think, by saying that we have to be careful to think of these cluster transfer or knowledge transfers or analogical reasoning or more specific instances of these kind of transfers as confirmatory in the sense of the context of acceptance. But I was a little bit worried, so just issuing a word of caution here, that when you discuss the pursuit worthiness at the end of, I think, the slide just before this one, you had at the end, you mentioned inductive support. And as examples, you mentioned Evans and Thibault's inductive triangulation, which the way I read them, it's not about inductive support for having reasons to pursue a research program, but is meant to be in the context of acceptance. So inductive support, yes, but what is it inductive support for? Is it to accept a theory or to pursue a theory? And I think that I would just, I'm very much concerned with the word here, an important distinction.
Yeah, so thank you very much. So that was put on purpose actually, because
To trigger me.
no, no, sorry, no, sorry. No, because exactly. So Loudon introduced the distinction as in the context of justification between acceptance and pursuit. The more recent debate tries to articulate that maybe it's not to be confined to the justification camp. And on the other end, not only here, it seems to be the case, I think we mentioned, I don't remember where, here, when Bartha think about this notion of epistemic support. So broadly speaking, let's put it this way, we are very much into the view that this kind of reasoning is useful to evaluate the pursuit worthiness of a certain program. But at the same time, maybe we're relatively more optimistic than you seem to be with the paper with Karen and Ilse on the fact that so we were relatively persuaded by this idea of inductive triangulation in the sense that even in other contexts which we seem to be more controlling, because of course quantum gravity seems to be a particularly complex environment to think about, you need to account for this kind of inductive triangulation, and so that analogical reasoning may provide some, as Bartha put it, modest degree of epistemic support. But I completely agree that what they were trying to do there was that of providing criteria for against your skepticism on analog gravity, and I think they mentioned fusion in stars as a possible way in which you construct inductive triangulation without any direct empirical access, right?
Yes. Yeah. So okay, we should discuss this.
Yeah.
But just to note, I'm on board with extending the pursuit worthiness into the context of discovery. That seems perfectly reasonable to me.
Exactly.
Obviously, it concerns heuristics and so on and so forth. So I'm fine with that.
Okay, so Anissa, as a follow-up, and also the last question, and since we started 5 minutes late, I think we're good time to, yes.
This is just a charitable rereading of the first bullet point. I mean, this is some kind of possibility I think you're hinting at here. I mean, maybe Evans, Thibault, Napo, that's not the right resources, but then the Bartha definitely. And that is standardly taken to be part of perceived worsening. That one reason why you find something to be perceived worsening is because it's plausible. And now I can ask.
You would put a possibility argument out of the perceived worthiness?
I think plausibility often belongs to perceived worsening as well in some way. I would say not necessarily just to acceptance. I just want to say I agree with this fourth point, but maybe not with the references. Yeah.
Okay. Yeah, sure.
And sorry, and now I can ask a question. Actually, more of a comment on the conservatism discussion here. I agree with Elisa that there's something rational about this, of course, very rational. And I just want to add, conservatism doesn't even have to be boring, because of course there's a lot of different senses. Boring. I mean, there's a different sense what you mean by conservatism. And there's this notion of Wheeler, of this daring conservatism, that you kind of really just take seriously what you have, and just work with what you kind of know and what is secured, but then you're very consequential about it. And in that spirit, even string theory, at least according to Alexander Bloom, with a very nice paper on this, is conservative. And so Pace, also Carlo Rovelli, who just wants to claim gravity is conservative, right? And something. And so it's just, according to Bloom, I think it's also rightly put, if you don't have empirical data, the way you can just be conservative in the sense that you can just work with what you have and just kind of use, I think, as you rightly point out, this kind of all these methods of cluster and knowledge transfer and so on. But it doesn't have to be completely, that you're just moving or like one epsilon from your point you're at. It can also be quite impressive. Yeah, I don't know.
Completely.
Yeah, sorry.
No, completely. So, there's always a blend of conservativeness and innovation in these approaches, and based on how much you're willing to make, to emphasize role principles. So we have Smolyan on the one hand, who's very willing to explore different routes in which principle seems to be playing quite a remarkable role.
Yeah.
And so the degree of innovativeness is quite evident. And Odo's also dynamic coherent would be a case in point in which you really want to build on the physics you already know.
Exactly. Yeah, and no, I agree. Yeah.
One last follow-up by Maria.
Okay, maybe I was not clear in the commentary. I'm all for conservatism. My point, I think we should respect the work we have, and I think we should pursue and utilize all the tools that we have. That was not something I was debating at all. I was more questioning once we have all of our candidates are conservative, and we want to decide now which ones to pursue and prioritize. Since we have knowledge transfer in them, if we always ever go for the one that contains or transfer the most possible amount of knowledge, then I might be worried about it being too rigid. But I'm all for conservatism.
Yes, I completely agree. That's the reason. I mean, this is also the reason that is outlined by the alternative argument by Stanford, that you build on physics that you rely upon, which is most likely not to be the one to rely upon. So yes.
Great. Then let's thank Emilia again.